All right. Hi, everyone. My name is James Thomas, and I'm here to talk about Fleet, a framework for massively parallel streaming on FPGAs. This is joint work with my advisors Matei Zaharia and Pat Hanrahan at Stanford. So FPGAs in data centers are growing. There's growing use of them in industry among companies like Microsoft, Alibaba, and Amazon. But programming them is actually quite difficult, especially for the software developers who are used to writing data center style applications. It's quite difficult to work with the existing hardware development toolchain. So we're trying to attack this programmability problem for a specific domain. And that domain is state machine based stream processing. So this is where each token in an input stream affects the processing of the next. There's essentially data dependencies there. Many important analytics applications have this quality, including parsing of various input formats, regular expression matching, compression, and machine learning inference. And the easiest way often to get high throughput for these sorts of state machine based stream processing applications is to process multiple independent streams of data in parallel with different processing units. So let's take a look at this massively parallel streaming model. You can see an example here of a string processing application where there is actually a dependency among successive characters in the stream. So maybe this is string search, for example, which is pretty hard to trivially parallelize by sending each character, let's say, to a different processing unit. So the single processing unit by itself might be pretty small. It doesn't fill up your whole FPGA. So what's a way to get better overall system throughput and utilization of the FPGA? Well, it's to add a few more processing units, and those processing units are processing their own streams of data. So this model is actually quite general. For example, if you have one big input file, and that file is your only source of input, you can split that up into multiple segments that can be processed as separate streams by different processing units. This is often possible, and this is exactly what systems like MapReduce and Spark and so forth rely on to do distributing processing and on clusters. So we built a system called Fleet, which is a language and compiler for this massively parallel streaming model on FPGAs. And the language is an extension to the Chisel HDL, which is embedded in Scala, and our language is also embedded in Scala, and it's oriented around token-based state machine streaming. So it's productive for developers without sacrificing control over performance. And the reason for this is it adds features for token-based state machine stream processing, but it still is based around this Chisel fairly low-level HDL that gives you sort of full control over exactly the hardware that comes out. So the compiler for the Fleet system, it takes a processing unit or PU in our language, and it generates many copies, a design with many copies of that processing unit, as well as a memory controller that feeds the processing units with their own input streams and also drains their output streams and writes them out to memory. So this is an overview of the entire system. We can see here you've got a Fleet processing unit written in our language at the bottom, and then the compiler will take that. It'll generate a design with many copies of the PU, as well as those input and output controller pieces that are reading each separate stream for each PU, and then writing each separate output stream as well. And these input and output streams are coming from the DRAM that's attached or on the same board as the FPGA. So here's a simple example of a Fleet processing unit that'll give you the rudiments of the language, and then we'll go into more details in a little bit. So this is a processing unit to do CSV parsing. So as you can see here, the number of bits in each input token is 8. So your input stream is basically broken up into tokens of just 8 bits or 1 character. And the output token size is also 8 bits. That's what's expected to come out in the output stream. And then we have a single register here for the current column that we're at in our CSV parser. So at a high level, essentially what this processing unit is doing is it's taking a simple CSV without any fancy stuff like quotations. This isn't a comprehensive parser by any means, and it's just producing all the everything in the third column of the CSV to the output, and it's discarding everything else. So the output is a reduced version of the input. So what this is doing, you can see this input identifier here refers to the current input token. Because this processing unit fires for every single, it fires once, it executes once, this logic you see here for every single input token. So if the input token is a comma, well, we increment our column because we're moving to the next one. If the input token is a new line, we make the current column 0 because we're going to the next row. And then, of course, if our current column is 2, if we're on the third column, we emit whatever we've seen in our input right back to the output exactly as we intended. So that's a simple processing unit there. So now to sort of step up and summarize the language as a whole, essentially for each input token, we have this while loop concept, and I'll show an example of this in a little bit. Basically, iterations of the while loop, if it exists, are going to be executed until the loop condition is false, and this is for each input token. And then there's a final iteration, what we can call like the post-while iteration, for any code that's outside the loop. So remember in the previous example, there was no while loop, so for each input token, you just executed that one iteration of code, all of which was outside of the, there was no while loop, so it was all outside of the loop. And then furthermore, we have a BRAM type for block RAMs. This is a basic primitive for denser storage that's available on basically all FPGAs, and we allow you to instantiate this in Fleet directly as well, but you're restricted to one read and one write per instantiated BRAM per iteration. And this sort of matches the actual capabilities of the block RAMs on FPGAs, which they have a limited number of ports, and that includes only a single emit per iteration, since whatever you emit goes into an output BRAM as well. And so we assume that the users have adhered to this restriction, and that's actually checked by a simulator. So we can run your Fleet PU on input traces, and we can make sure that they only do one read and one write per BRAM per iteration. So here's an example of a Fleet processing unit that uses some of the extra features that we just talked about. So this is one that computes histograms on blocks of data. So still the input token size is 8 bits, and the output token size is also 8 bits. But here we're looking at blocks of 100 integers, essentially, that are 8 bits in size, and we are computing histograms for one histogram for each block of 100 inputs, and we're essentially doing a count essentially of how many times each distinct value, there's 256 distinct values, how many times each one appeared in our set of 100, and then once we've hit the 100th element, we want to emit whatever's in our histogram, clear it out, and then move on to the next block of 100 in our stream and keep going until the stream is over. So just to look at the main body of this code, we have this block RAM type instantiated here to actually store the histogram, the actual counts. That's important to note. And basically, most of the time, the counter is not at 100. We're not at the final element of our block, or in reality, this is actually the next element, the first element of the next block is when this input counter would equal 100, we trigger this part of the this block here. So normally we don't hit that case. Normally we're just hitting this case where you're incrementing whatever the appropriate cell in your histogram is by 1, and then you're updating your counter. And then when you actually hit 100, when you're at the end of your block, you go through the whole histogram with this while loop. So the while loop essentially pauses the stream. We say we're waiting on the first token of the next block. We've paused the stream. We're going to go through the histogram, emit everything from the histogram to the output, clear the histogram to 0, and then this code outside the while loop will now also execute for that token, which is the next one, the first one for the next block, and it's going to take that token and appropriately update the histogram, which has now been totally cleared, and start it off for the next block of 100. So this is sort of the idea of the logic here. So the nice thing about our system is that we're able to give you predictable performance for all Fleet applications. And the reason, and in particular, we're able to guarantee a throughput of 1 iteration that includes the while iterations as well as that post-while iteration I was talking about, a throughput of 1 of those iterations per FPGA clock cycle due to the restrictions we've placed on BRAM use. We essentially force you to only do 1 read and 1 write per BRAM per per cycle. We expect that you adhere to this, and the compiler assumes that you've adhered to this. And the thing with HLS tools is they can't assume this. They're assuming you're giving them any, possibly valid C code, with no restrictions. So they have to analyze it and see, okay, are you actually just doing one read and one write per blockgram? Otherwise, they have to add extra pipeline stages to possibly handle the extra reads and writes to each blockgram, and they have to also add pipeline stalls. So this is, often a difficult challenge when you're writing these sort of state machine type applications, which at HLS tools, we've tried to do exactly this. And if you just write the standard C code, the compiler will not be able to figure out that you're only really using these blockrams. You're reading and writing to them once per cycle, and so they will create these longer pipelines unless you add pragmas and do a lot of extra work like this. So this is a little less intuitive, doing that kind of thing is a little less intuitive for developers, and we're sort of saying, okay, we're going to raise this important concern to the top of the whole language, and we're going to force you to think about this. But when you do think about this, ensure that your code adheres to this restriction. We'll guarantee that we can give you this good throughput. And the actual pipeline that we generate to give you that throughput of one iteration per cycle looks like follows. Once you have the restrictions, it's pretty straightforward. The reason you need a two-stage pipeline is because VRAMs have a latency of 1 generally when you read from them. So when you supply a read address, it takes an extra cycle for the data to come out. So you have one stage where you're supplying a read address, another stage where you've received the output data, and you can use it, and you can also forward it back to the previous stage. This is a standard technique of forwarding that's used in pipelines and computer architecture, and it's pretty straightforward to set that up and get that all working to guarantee you a high performance pipeline. And of course, since we're a lower level of abstraction, we're sort of closer to the RTL level, you may still need to add registers in your code to ensure you get a good clock period, but you'll never have these sort of pipeline, long pipelines or poor initiation intervals in this sort of HLS terminology because of the restrictions we've imposed. So now moving on to the memory controller that our system has. So this is one of the keys to the high performance we're able to get. Essentially what it does is it feeds multiple processing units in parallel. And the reason this is needed is because each processing unit has an input VRAM where it buffers up input data, input tokens that it's going to be reading. And that VRAM has usually a port size or data port size of about 32 bits. So it can only take in 32 bits per cycle, but the data coming from the memory system, from the AXI4 based memory system, in particular on the F1 platform that we're going to evaluate on, is 512 bits per cycle. So if you're just feeding a single processing unit at once, you can get up to 512 bits per cycle from the memory system, but you can only write 32 bits per cycle into the processing unit. And there's no way to add extra VRAMs to each processing unit to make it have an effectively larger data bus because we have so many processing units in our applications, as you'll see in our evaluation. So that would cause us to run out of VRAM resources. So instead, what we need to do is we need to have these things, instead of sequentially feeding one processing unit then moving on to the next, we need to have these things called burst registers, which essentially hold 512-bit chunks that we received from the memory system, and they hold many of them. In this case, we're looking at 16, and then each one is draining itself to a processing unit 32 bits per cycle, which is the data bus width of the processing unit. And if you have 16 burst registers, each one is draining out at 32 bits per cycle. That's a drain rate of 512 bits per cycle, which matches the rate at which you're receiving data from the memory system. So this is what sort of allows us to match up with the performance of the memory system. And since we're reading these different streams for each processing unit from the memory system, we can really saturate it and max out its performance. So just to talk about the throughput we're able to achieve with the memory controller, that's about 27 gigabytes per second of input read throughput on the Amazon F1 platform across 4 DDR3 channels that are available there. And we wrote some RTL to check, okay, what is the peak achievable throughput at 125 megahertz, which is the frequency at which we ran all of our designs, and that was 30 gigabytes per second of input throughput. So we're pretty close to the peak, and that's throughput you get for reading just a single stream. Here we're reading a bunch of different streams in parallel for each of the different PUs. So it's sort of a more complex memory controller, and we're still able to get pretty high performance. And then of course, if you produce a lot of output in addition to reading input, that's going to compete with the input for bandwidth, so then your throughput is going to drop. But it's 27 gigabytes in the best case. So just to do a evaluation here, we looked at 6 different applications. One was JSON parsing, integer compression, decision tree, Smith-Waterman fuzzy string matching, regular expression matching, and Bloom filter construction. So you can see the number of lines of code for the Fleet processing unit is pretty comparable to C, CUDA high-level synthesis lines of code. And this is because we're handling a lot of important functionality for you, like input buffering, output buffering, the memory controller piece. So even though you are working at a sort of lower level of abstraction with Fleet, closer to the RTL level, it is pretty simple to generate a fairly complex and performant application. So just to look at some performance numbers for these applications, we were able to put hundreds of PUs on the Amazon F1 device for all these different applications. We're able to get a pretty nice performance per watt improvement over a V100 GPU, top of the line GPU available in the EC2 cloud as well. The one case where we didn't get as much of an improvement was with the decision tree inference, and for this one it was because there wasn't too much compute per access to BRAM, and on the GPU there's a lot of SRAMs that have pretty high bandwidth, so that's why we believe we lost out there. And most of these applications are actually bottlenecked on the memory system, so that means if you added a better memory system, let's say high bandwidth memory or something like that to the F1 platform, these would go even faster. So that's pretty nice that we were able to max out the memory system there. So just a summary of our comparisons to CPUs and GPUs. 36 hyper-thread CPU that we looked at on the Amazon cloud was generally 5 to 10x worse in raw performance than our Fleet applications. And then it was 50x worse in performance per watt, and all these CPU applications were compute bound. And for the V100 GPU, we had similar raw performance in general to the Fleet applications, but 5x worse performance per watt, as you saw in the previous slide. These were also compute bound, and you can see the full experimental results in the paper. So the general reasons for the speed up over CPU and GPU was just we had a large number of processing units, much larger than the number of cores on the CPU or number of SMs on the GPU in many cases. We were able to fuse what were effectively multiple CPU and GPU instructions into a single FPGA cycle worth of work. That's always a way that FPGAs can win here. And then we also didn't have a penalty for control flow divergence, which you get in GPUs as well as in the CPU SIMD setting. We didn't have that on the FPGA because we generated the logic for all these processing units. So when comparing to Xilinx HLS for some of these applications, the memory controller performance was really what hurt the HLS tool in this case. And essentially, as I described before, with our memory system feeding all the processing units in parallel, the HLS tool doesn't generate a memory system that does that. Instead, it feeds the processing units sequentially. And as I was saying there, that becomes a pretty big issue because each processing unit only has maybe a bandwidth and input read capacity of 32 bits or 64 bits per cycle. So you can't match the rate available from the actual memory system. And in fact, this overall memory controller that was generated from the HLS tool was about 10 times slower than ours, which really bottlenecked all the applications. So in conclusion, we present Fleet, which provides an intuitive token-based stream processing model for FPGA developers. It allows push-button generation of high-performance, multiple processing unit FPGA designs for this sort of massively parallel state machine style streaming model that we've talked about. So thank you for listening. You can get in touch with me at the email you see there, and you can check out our code at the URL there as well. Thanks again.